Good afternoon, ladies and gentlemen. It's Monday, 16 May 2022, and I'm really happy to welcome all the people that joined the EPIC online meeting number 13 of 2022, as well all the YouTube tribe. Most of you already know EPIC, the European Photonic Industry Consortium. For those persons that doesn't yet know us, EPIC is the largest no-profit industry association with nearly 800 members working in the photonic field, from laser to micro-optics, from display to quantum technologies. We foster a vibrant photonics ecosystem by maintaining a strong network and acting as a catalyst and facilitator for technology and commercial advancement. EPIC publishes market and technology report, organizes a technical workshop and B2B roundtables, supports EU-funded proposal, advocacy and lobbying, as well education and training activities. He works also pushing roadmaps and standard, as well pavilions to the major exhibition. Today we will speak about micro and nano satellites in the new space. Society now takes the day-to-day benefit from space, from weather forecast, ubiquitous communication and navigation system, as well immediate response to natural or man-made disaster. Indeed, the functioning of the developed world is becoming really dependent on space to provide all the economic and societal infrastructure. Let's say that small satellites are more or less a state of mind, just a simple physical parameter. Today, in many instances, small satellites compete and sometimes even surpass the capabilities of traditional large satellites, but at a fraction of their cost. Today, we will speak how photonics is really enabling all these technologies. And as I said, EPIC, we are trying to cover all the application of photonics. In the last 2 years, we organized more than 100 online technical meetings. In the next weeks, we will speak about other topics like co-packaged optics, VCSELs, plastic sorting, and so on. As well, we prepared also the next season. And here I would like to highlight 3 interesting meetings. Satellite quantum communication, Earth observation, and metamaterials and meta-lenses that are clearly connected to this meeting. But let me introduce my colleague, Jérémy Picot-Clémente, that helped so much in organize all these events and specifically this event. Jérémy.
Yes, thank you, Antonio. Good afternoon, everyone. So here you can see the EPIC team made of 14 people, all passionate by photonics. So yeah, this team manage and support all the ecosystem with their technology knowledges, market reports, proactive networking by organizing physical and online events and easing the access to market of for our members. And we give also support in HR with specific website dedicated to jobs in photonics, and we support also the development and the investment in this industry. And yeah, so this event is sponsored by Acktar Advanced Coatings, which is a world-leading company in light absorption materials and coatings, and provides a solution for the suppression of straight light in invisible sphere and wire wavelength. So if you need to be put in contact with someone here or for anything else, any question, feel free to contact us. You have here our email address, Antonio's email address and mine, and you can also find us on LinkedIn, of course.
Okay, so before to start this meeting, as usual, I show which are the companies that registered in the meeting today. Here we see really all the stakeholders of this of the new space economy. We have a free space agency as well a rich overview and a rich basket of end users, from automotive, agronomical remote sensing, defense and security, infrastructure remote sensing. Clearly, all the ecosystem is complemented by free space optical communication, photonic integrated circuit, complex photonic system, lasers, optics and micro-optics, quantum technologies, testing and measurement system, multi and hyperspectral system, and so on. Last but not least, are very important to name also the R&D structures, as well the Agency for Market Intelligence Consultancy and Investment, and the association and the Digital Innovation Hub. The agenda of today, the panel of today is made of 5 great friends. We will have Marco Di Clemente, the head of technology unit of the Italian Space Agency, Eduardo Margallo, the CEO of Ommatidia, Boris Hecknor, the senior manager of new venture at SHOT, Fabrizio Preda, the CEO of Nereos, and finally, but not least, Stefano Bonora, the CEO and founder of Dynamic Optics. So I will stop now sharing my screen, and I would really like to introduce the first speaker, Marco. It's really a great pleasure and a great honor to have you here. So please, Marco, start your presentation, and we can start officially the meeting. You go to presentation mode, please.
Okay, thanks a lot. Can you hear me?
Yes, clear.
Okay, thanks for your kind introduction, Antonio. I will briefly introduce the activities ongoing and future activities on photonics at the Italian Space Agency. This is the overview of my talk today, just a brief description of the approach that we have in general for all kind of technology developments. Then we go specifically through photonics application with an overview of ASI activities and then the conclusions. This is the general approach when we speak about technology development. There are basically three main drivers. The mission pool activities that are generally driven by requirements, challenges, or recognized need from a specific need that we need to foster for a specific mission. Then we have the technology push development that is driven by disruptive and innovative developments coming from most of the time from the R&D sector, from universities, small and medium enterprise. And then, of course, we in the last few years, there is this new trend that is generally called the space economy. That is most of the time it encompasses developments driven by the value chain, so from research to space infrastructure. We define the technology unit of the Italian Space Agency, what we call a multi-step approach. STEP is the name of our technology program. That is basically organized in three main steps, with at each one correspond a specific funding program. So we have the step one for low TRL development, for the development of disruptive technologies. And generally this kind of approach is focused on small, with a small budget, a small amount of resources, but with a lot of projects. Then we have the step number 2, that is for a scene to overcome the death of Valley of Innovation with a target TRL up to an increased level of resources associated to each project. And the step number 3, that is devoted to qualification testing of technologies, and including, of course, IOV, IoT activities. The goal of all this technology development is to have the right technology with the right level of maturity with the right time, so to be used in our missions, in ASI or international missions. Specifically, the interest for photonics in the agency, of course, regards most of there is a variety of possible applications. For example, just to say something, Lidar, laser metrology, structure and thermal behavior, OCS, onboard data handling, and much more. And in the last, let's say, 5 years, we, as ASI, we funded most of these areas with the specific attention to ensure the technology maturity of photonics-based components, which are the main opportunities coming from photonics technology. Since it is progressively expanding in many terrestrial fields, the sustainability is rather well recognized, with, of course, the need to spin in from technologies used in a terrestrial field to space. The resources also are always a problem dealing with space, but the use of photonics can, of course, represent a technology leap, because, of course, due to the best efficiency in terms of energy, the reduction of mass, dimension, and that handling, and flexibility given by photonics, even for new kind of missions. There are some challenges that, of course, we need to face. First of all, the availability of components, especially for space qualified components, is always, of course, a problem to be understand. There is a need to accommodate new components based on photonics in traditional or in already existing architectures, and then, of course, this is a need for the R&D and the need also to develop new design solutions. And last but not the least, there is a problem of dependability, because as you know, space is not cheap most of the time. It requires, especially for some specific missions, there is a need to use qualified processes, and of course this takes time and resources. The main interests in photonics are deal with the communications. You already mentioned, has been in the introduction, optical communication, inter-satellite or intra-satellite communication, microwave photonics for RF links, so the use of photonics with in combination with the radar system, and quantum communication. Regarding sensing, we have a recognized leadership in Italy regarding LiDAR, especially high power LiDAR in for Earth observation. Radar based on photonics components has been also have been developed. Optical sensors or lab on chip. Here, just a few examples of some of the activities ongoing on photonics. Most of these activities have been funded or are currently ongoing with Italian partners or universities, small and medium enterprise, research centers, and so on. We are integrated circuits or space qualified packaging. We are working on remote sensing satellite platform based on photonic components, quantum communication for space, mostly regarding the quantum key distribution and photonics for space quantum com, and OCS sensors, specifically the development of a new gyroscope based on photonic components. Quickly, these are the conclusions of my talk, just to introduce you the scene, let's say. As I say, the photonic technologies can be used in scientific and commercial payloads, in satellite and launchers at all levels, so systems, some systems and components, but also at the ground segment level. The activities at the Italian Space Agency in photonics encompass a research project spanning from low TRL to IOV/IOD missions, and in these regards, I can mention the new CubeSat program that we started a couple of years ago. We selected through a national call 20 missions, and most of these missions will be also used to perform IOV/IOD of critical technologies. So the calls and the opportunities have been defined even to enhance spinning activities, and specifically in this field, I think it is really important. This is the end of my talk. So I thank you for your attention. Thanks a lot.
Thank you so much, Marco, for, I would say, for the great list, the wish list, or this is really a buying list, and also for the opportunities. Maybe while I'm asking for questions from both the people in the Zoom room and the YouTube participant, I make my first question. You explained about Italian Space Agency needs. How is the position of the ASI with respect to ESA, I would say? So there is a coordination between ASI and the other agency, and which could be the opportunities all around Europe for photonics?
Yeah, thanks for your question. Of course, there is a strong coordination between ASI, the other national agencies, and ESA. So when I mentioned ASI activities, actually some of them have been funded by ASI, but are currently ongoing with ESA programs, like GSTP is one program devoted to technology development. In ESA, for example, photonics is one of the topic that is harmonized regularly about in every 3-4 years through the Technology Harmonization Advisory Group. That is a group composed by ESA, by the representative of all national agencies, with the aim to harmonize technology developments and to avoid, for example, duplication, to avoid overlapping of activities. And within this group, we are able to define the roadmaps for the specific technology that every national agency can consider as a reference. And this is, of course, done in order to maximize the effort in this cooperative approach. For this, the group is called TAG, Technology Harmonization Advisory Group. And of course, I'm available for if you need some more information, but you can also Google it and you can find something more.
Okay, thank you so much, because this is a really interesting information. Here, I see that we have a lot of potential supplier about what are your needs. So nobody would like to comment or to ask some question to Marco? Come on, don't shy. Maybe I go further with another question, another technical question. I saw that you made the differentiation between intra and inter-satellite communication. Could you comment a little more, explain a little more, which is this differentiation?
Okay, we mean for inter-satellite link, of course, the capability of a satellite to communicate with the ground station or with another satellite in space. So it's a space-based communication, that free space communication, and this, of course, a technology really important, for example, dealing with constellation of satellites. So the capability to enhance this kind of network in space can, of course, reduce the effort on the ground station that can communicate the command to just few satellites of a network, of a constellation, and then this command can be shared through this the capability of the inter-satellite link. That, of course, have some specific requirements in terms of pointing accuracy, of stability of the two systems that need to speak each other, let's say. For intra-satellite communication is the communication between different units of the same satellite. And this can, of course, nowadays, this kind of communication are based on harness. In the future, could be based on optical, fiber optics, or on wireless signal, even based on light. And we have already some, and this, of course, can enhance the speed of communication, can reduce the mass. That is always the main driver dealing with space. We have already some projects ongoing involving, for example, Scuola Superiore di Sant'Anna, Thales Alenia Space, both with some national projects funded by ASI or through ESA projects, even funded by ASI. Coming back to the first question. Oh, so this is the main difference between these two points.
And which is the trade-off between special devices developed for space with respect to standard devices that are maybe widely used on Earth? I think that when we are speaking about small satellites, somehow we can also release a little the specification about roughness and lifetime of the satellite. We can think on a short lifetime of the satellite itself.
Yeah, of course. The trade-off mainly depends on the needs of your mission and the main requirements. Let's say, if you generally for small satellite, for nano-satellite as CubeSat, the standard, the requirements are less stringent than for a classical, let's say, satellite. And this means, of course, that you can relax your specification. In our perspective, in ASI perspective, this relaxation cannot be done. We need always to preserve the safety of the system. We don't want to create a new debris. We know that this is the main. So even when you use, for example, not space qualified components, we defined a specific policy, for example, for testing, for screening of these components, in order to avoid, of course, or to the risk of losing the system. Then we have also, this is why we have IOV/IOD missions that are, in our perspective, acquire space knowledge or space experience of components, even not specifically developed for space application, that can be considered as a payload, not as let's say, the mission itself. And in this perspective, we can also accept a failure. That is, that not means the failure of the mission, but a failure of an experiment, as done, for example, in a ground-based facility. We developed in the past specific assets that are devoted, for example, to perform, can be used to perform IOV/IOD experiments. I can mention Space Rider system. I can mention ION system developed by the Orbit. We have a huge number of missions of CubeSat that we are going to launch. All these missions can be used to perform IOV/IOD, even without, let's say, all of the specifications that are generally considered in a traditional mission. Then once that you acquire knowledge, experience, you can test exactly as your component works in a space environment. The goal can be used also, of course, to translate these the components in a institutional, traditional mission. So even with the level of confidence increased by your IOV/IOD activity that you perform.
Okay, thank you so much, Marco. And okay, I see that Tracy is the EPIC specialist of market report. So Tracy, what is in your mind?
Thank you, I think, Antonio. Marco, thank you so much for your presentation. I have a couple of quick questions for you. So are you focused more on defense, traditional defense, or are you also focused on communications, such as linking 5G communication to the satellites?
We are most focused in this specific time to communication, to even 5G communication is an asset for us. Yeah.
Okay, that's wonderful. So with that, there are timing issues, of course, which we are going to be discussing a little bit later here. But are you also looking at some of the photonic solutions for communications? So traditionally, this was RF, as you mentioned, but there are, for example, there's photonic beam steering applications that can be used now instead of the traditional RF, which cuts down significantly on the amount of power that is utilized and also size, weight, and et cetera. So are you looking at photonic beam steering? Are you looking more at free space optics, or what can you tell us?
There are activities. We have some research activities dealing with beam forming based on photonics. That are ongoing. There are some research activities in Italy. So the main, let's say, the next step would be, of course, to use these technologies in a space, in a real system in space. Now we are working at with R&D on Earth. In the future, we already plan some activities in order to test even in a space environment this capability.
Thank you. I have a couple of contacts for you that I'll send you later. Thanks so much, Marco.
You're welcome. Thanks a lot.
Okay. So nobody else would like to ask or to comment. I think that for the moment, I thank so much, Marco, for the—
Antonio, sorry, excuse me. There is a question in the chat from Intel.
Okay, Intel. So is Roger. Please go ahead, show yourself and make your question. I don't see And I see also another question from Florian from XR Nanotech. Maybe Florian, you can go ahead with your question.
Yes, hi. I wanted to ask whether you're looking into multiple channels per data link in an optical link for your communications. Or
yeah, this could be a quite interesting development. Currently, at the moment, we don't have any specific project or activities ongoing on this specific topic, but of course, it's an interesting activity because can enhance, of course, the data rate. That is always a problem.
Thank you.
Okay. So, Roger from Intel, I think that is not ready to ask his question. Maybe I read it.
He may be muted.
Okay. I read the question and okay. Roger is asking if these satellites are for EAE orbits, with what data rate and modulation format do you anticipate for intra-satellite communication, direct or coherent modulation? This is a quite specific question.
Yeah, maybe on this point we can come back privately for. Regarding the orbits, most of the examples that I mentioned are focused on a LEO orbit, low Earth orbit, so close to the Earth. The optical communication for deep space are, of course, something more difficult to achieve, and probably not in the next few years, I would say.
Okay. No other comments. I will say that now maybe is the time for Marco to take a breath after this set of questions. And I introduce Eduardo from Ommatidia. Ommatidia is one of the biggest producer of Lidar. And I think that for space, there are a huge amount of Lidar necessary for several purposes. So Eduardo, the floor is yours.
Thanks a lot, Antonio. Thank you for the opportunity to be here presenting Ommatidia today. And yeah, let me just jump onto the presentation. You can see it, right? Perfect.
Go ahead, Eduardo.
Of course, you all know what LiDAR or laser radar or LiDAR is. It's essentially a light-based analog to radar, and it gets many names depending a bit on the application. So when people talk about LiDAR, typically they talk about, let's say, navigational ranging and not very high accuracy. But when it becomes specific about metrology, normally the terms LiDAR or laser radar are employed. And this takes us a bit to the different solutions that are being used to measure distance to objects. As many of you know, there are two main trends. One is time of flight, which is the established modality where you just send the pulse of light to the objects, wait for the light to come back, measure the time. And more recently, something which is done very often in radar is being applied also for LiDAR, which is FMCW LiDAR. And there you use a chirp, variable frequency signal, and you measure the frequency difference between the light you get back and your local oscillator to determine distance. So the big advantage of continuous wave systems is that, of course, you can use all the time that's available for imaging to illuminate the scene. And that often translates into many more sensors, many more photons and much more resolution. The problem is that all FMCW systems so far, they are a single channel, just looking with a collimated beam to the object that you need to scan somehow. And this is a bit of limitation. For example, with time of flight, there are already cameras that have parallel sensors and which allow for flood illumination and high resolution in some ways. So that's what we are doing at Ommatidia. We are doing continuous wave, frequency modulated continuous wave LiDAR with massively parallel detection and illumination. We believe we are learning from nature in doing so because, well, our sensors look a little bit like the eyes of insects, compound eye of insects, and we are trying to increase the number of elements going from, well, let's say, simple animals like flies to very agile and precise predators like dragonflies. And our sensors are really going the same way, from 500 elements in our first generation to 50,000 elements in the current device to 500,000 elements in our next generation. And with this, we can really go to very high resolutions with long range and very good distance accuracy. We have applied this already to some problems in space, and one of them is an instrument that we have been developing for ESA, which is meant to measure the shape of large deployable reflectors. These are parabolic antennas, parabolic reflectors that are too large to fit in current launchers, and they need to be folded. And once unfurled or unfolded, you need to well, know what the exact shape is to make sure that they work properly. And this is what our instrument does. I mean, here you see it, I mean, open with all the bits and pieces, and it's a very light instrument. You have the 3D receiver here, and then some illumination and collection optics to support it. So this project is now coming to an end in the coming weeks, and we have already demonstrated that we can measure about 100 points with very good repeatability. We are now finalizing the adjustments and calibrations to present the final data also in terms of absolute accuracy, but typically we are able to resolve down to 10 micron accuracy. We have applied this also for a commercial metrology instrument. It's a laser radar, again with 128 channels in this case. We provide interferometric absolute distance measurement at high speed with good resolution. This is being applied now in aerospace, again for parts for space projects, antennas, also composite structures. And more recently, we are also seeing some use cases in civil engineering, for example, where what matters is not so much the dimensional accuracy, but rather the ability to measure small displacements and vibration. We have used, I mean, just as a few examples of use cases, we have used this instrument to measure the resonant modes of the parabolic reflector in collaboration with Airbus Defence and Space. And you can see that, well, it's able to give you a very nice spatially resolved picture of how your antenna is vibrating for the different resonant frequencies. Just to give you an idea of how this works, well, this is the instrument. We are scanning here a guitar with a 0.5 second integration time that gives us a resolution in frequency of 2 Hertz. And you see that in a few seconds, you can scan the full guitar. And you see, well, the resonant modes on the right, the frequencies, and the spatial distribution of the energy in those modes too. The big advantage here is that we are able to go very far to 50-meter range, work outdoor, and I mean, it's also good for large structures, right? We are applying also for automated metrology on the ground, but we are starting now a project for the application of this technology in orbit. And we have now also projects starting more focusing on GNC, so navigation and situational awareness, where this technology is being applied not for very high accuracy measurements, but more for the LiDAR type of use cases. This is a project in collaboration with TNO. They are providing the optomechanics. We are providing the LiDAR technology. And that's a summary of what we are doing at Ommatidia in space. If there are any questions, I'll be happy to answer them.
Thank you so much, Eduardo. This was really an interesting view of a LiDAR going into the space. I think that this is really impressive. So I just ask if there is any question, or while the people are elaborating this information, maybe I make a question to you and also to Marco. Marco named before about to avoid to create debris. So we have debris in the space. Could be LiDAR an option to detect debris and potential damages coming from debris to existing satellites? So this is a question for both Eduardo and Marco. What do you think about these ideas?
I don't know, Eduardo, do you want to?
You may have a broader view. What we have experienced in terms of applications of LiDAR for debris is mostly related to the orbiting. So missions where you want to address specific pieces of junk in space orbiting the Earth, and you want to bring them down. So then LiDAR can become very useful for navigation in the approach phase. I understand there are also efforts to use LiDAR to detect debris from the ground, but I'm not so familiar with those.
Yeah, if I can complement the point, of course, it mostly depends on the size of the debris, so on the capability, of course, but in principle, not in principle, also in reality, it is can be used. There is a capability to track from ground debris, even using light, using laser. Regarding the possibility to use laser for debris removal is also an interesting application, and very interesting, and has been also presented in some research activities. So mostly from a theoretical point of view, of course. Once is the theory. One thing is the theory. The other one is to develop the technologies, the capability to put in practice that theory. But in principle, specific, because of course the main problem for debris, for the very small debris, is that there is a certain difficult to remove with an active debris removal system. So you can think, for example, big missions to remove satellite or quite large debris, but for the small one that could be also quite dangerous for space assets, maybe we need to develop something more and something different. And laser can be the answer. Why not?
Okay, so great. So here we are really putting also the seed for new concept, for new development. I see in the chat that Alexander Teller from Acktar also made the question. Alexander, please do yourself.
Yes. Thanks, Antonio. Thanks, Eduardo, for your presentation. Very impressive. So we are specialized in the application of black absorbing coatings to, for example, to suppress scattered light and stray light in optical systems. So I'm always curious if you have any challenges to solve with the integration and the assembly of your LiDAR system, and if there is anything the photonics community that is present in the room can help with your system, with the realization of your system.
Yeah, absolutely. So when we are integrating our systems, there are a broad range of challenges we need to address, and some of them are, for example, in the area of packaging, photonic packaging, with solutions that are compact enough, which are performing enough and reliable enough for space applications. That's definitely an area where we are very interested in collaborating. And Another area is clearly also the scaling of this technology, not so much for space potentially, but definitely in other markets where volume and cost becomes an issue. So industrial markets, robotics, automotive, all of those need solutions which are highly scalable and can be produced at relatively low cost.
Okay. And I see in the chat that also, we have Roger from Intel with some issue with the microphone, but I see also that Ernesto from Scuola Sant'Anna has some comments. So just a recommendation, don't shy and talk with all the other participants. This is just a family meeting. We are just on the YouTube channel, but it's a family meeting. Okay, other question or comments? I see my new colleague, Antonio Castello. Welcome, Antonio. Which is in your mind?
Thank you. Yeah, I was curious also about challenges, but in this case, challenges about illumination. So, Eduardo, regarding illumination in the space, is there any difference compared with the kind of LiDAR we use nowadays in ground applications?
Well, an advantage in space applications that typically you don't have the type of restrictions that you have in ground applications, where eye safety often becomes, let's say, the main cap on optical power. And for some applications, well, this can enable longer ranges or I don't know, higher performance of your systems if you're able to drive, let's say, those powers. So indeed, there's space for the application of high power lasers, high power fiber amplifiers to access some requirements, some applications which may not be feasible without them. So I think it's more an opportunity than a challenge, but definitely the development of these components can open up a number of opportunities there.
Yeah, thank you. Thank you very much. Very nice presentation, Eduardo.
Yes, thank you so much. And sure, in the space, we don't have the absorption of atmosphere. We are nearly in the vacuum. So we are really much less problem in the beam propagation. Okay. So I will move to the next speaker because, okay, time is flying at the hand. So we are going into the space, we need optics and we need special material for optics, because I think that this is the key challenge. So I'm really welcome Boris Eichhorn from SHOT to learn which are the perspective for optical components in the space. Boris, the floor is yours.
Yes, hello, Antonio. Hello, everybody. Can you see my screen?
Perfect.
Nice.
You are our champion.
So what a pleasure to be here today and take off together with you. So my name is Boris Eichhorn. I'm working for SHOT on the corporate R&D level, kind of business development. And already last year, beginning of 2021, we started to see what is in our portfolio and in terms of solutions for the new space economy and what's going on out there, to create an idea and an understanding, and also to see how we can support and solve challenges. And today, I want to present you a little bit about our perspective and our solutions and the challenges we see. And I'll also try, of course, to focus a little bit on satellite miniaturization. So 3 sentences about SHOT. We are a global company in 34 countries, so we should also be close to you. And we have more than 17,000 employees. Last year, revenue, global sales, 2.5 billion. And we have these here on the right, these target markets. And as you can see, aviation, astro, and space is a strategic target market for us since very long, so a couple of decades. Next slide. This is just one slide also for introduction on the space economy. So on the left, these are the end applications that we are seeing. So security and defense existing since long, a lot of governmental spending into it. Telecom, a lot of movement here, as you all know, in terms of internet from space, these mega constellations, CubeSats and so on. Navigation and tracking, GPS, also known. Earth observation, because of the challenge of global warming topic with all those sensors that are now developed also. We see clearly here movement. Broadcasting and the evergreen exploration and scientific when it becomes fancy. On the right, we see here mega trends matched also to those end markets. So internet from space, we talked about it, coverage, to have global coverage, access to internet from space. Sustainability, green economies, so the amount of data increasing to hold people and institutions on Earth accountable for their actions and really improve here. Private invest, all these investors like Elon Musk and Bezos that are driving the market. Also, of course, the ecosystem of startups that is coming up all over the world that is supporting here a lot to really commercialize space. The importance of innovation. It's about new materials, and it's important for us. It's also about new technologies like 3D printing, miniaturization, as we talk about it today, to reduce payload. Then topic space ventures and future scenarios. That's that one I love, of course. Moon missions, Mars missions, and so on. Maybe a little bit more into the future. And yeah, also the sadly more political conflicts in a multipolar world. So here is already a first slide, what we see as a materials provider in terms of requirements. So of course, lightweight is a topic, reduce payload for those missions to save money. We have optical requirements because we provide a lot of optical components. So highest transmission depending on the application. On the other side, for some applications, you need also a stability against certain space radiation, be it solarization, be it particle radiation. Long component lifetime, usually in space, of course, again, depending on the application. These two here are about the delta in temperature from Earth to space, so a thermomechanical stability as well as a low CTE are important for some components like our Cerodo material to really have the best performance for the application. Breakage resistant, high strength, I mean, especially during takeoff, but also afterwards. Highest precision and hermeticity for packaging solutions. So we see a lot of those requirements. We can fulfill them depending on the products. And what we can offer is specialty class ceramic materials, as well as hermetic class sealed components to enable various applications in new space already. Let me talk to you about it in a moment, and by fulfilling these space-related requirements. So here we go. That's our overview on satellites, ground station, rockets, other ventures. So I can proudly say we are not only on Moon, but also on Mars with our products, and we are already working on the next missions for that. But today I want to focus on the left side, on the satellites. As you can see here, this is a long list of products and solutions, and we are working again, we also work on more. But let me shortly go through it, always having in mind the idea of satellite miniaturization and improvements. So first of all, Cerodo mirror substrates, that's something where we have a space heritage since 40, 50 years in space for telescopes and imaging. And now we are also seeing the market of laser communication for the communication between the satellites. We heard about it before. So that's something where we are offering our Cerodo mirror substrates, because with a high reflectivity they have and with a proprietary post-processing, we can also create very lightweight structures here to reduce payload. Glass substrates as thin protective cover for space photovoltaic applications. That's a very exciting product and solution from our side, because it's a blockbuster product. We can do it in high volume already. And yeah, it's actually a very thin glass, so it can be below 100 micron to protect the photovoltaic modules against certain radiation, while on the other side, increasing the transmission in the required wavelength. So with this approach, we can then, of course, increase and optimize the efficiency of the photovoltaic modules. And if you increase the efficiency, the idea is also that designers can then design the satellite smaller because less area creates the same amount of energy. Glass substrates for RF communication. We have here developed materials that have very good dielectric properties for high frequency communication. Flexinity Connect is another product which we are not only marketing in space, also on Earth. We believe here that we can replace printed circuit board with glass circuit boards. And there is another layer design with a structured glass that this material enables. And with that, we can then also reduce size, which is important for miniaturization, and improve the performance on the other hand. And also, if you need a long component lifetime, we believe that glass circuit boards can play a role here. Fiber optical light guides for calibration tasks and device alignment. So if you want a light-based calibration with a lot of design freedom, we have here space-ready products in our portfolio, already applied in space. Radiation hardened fiber optics. These are, for example, fiber optical plates that can protect sensitive components like photodetectors against harmful radiation from space. Then we have hermetic microelectronic packages, also a very important product for us here for space, where we have the protection against the harsh environment in space, gas tightness, vacuum isotopic, and these can then still enable the highest performance, highest transmission, for example, of the micro-optical elements or any kind of components that are packaged. Glass cylinder from hermetic sensor packages go in the same direction, also gas tightness here with a different form factor. Radiation-resistant optical glasses. Here we have a track record with NASA, ESA, many different missions with our optical glasses. Because of their radiation hardness, then they can also have and provide a stable transmission over a mission lifetime and over a longer lifetime. That's really important. And out of those optical glasses, you can also make spherical lenses, which we can do customized in very high precision for a lot of different space missions. And the last one on the list for today is the optical filters and coatings, for example, to be used in multispectral cameras for Earth observation. So that's a long list. We tried here with this sketch also to kind of align it schematically to a satellite. So as you can see, while the upper three products here are mostly related to the satellite body, you have here photovoltaic cover glass, protection of the modules. The other products here and solutions are addressing the sensor suite. So depending on Earth observation, laser internet from space, laser communication, other use cases, we have then products in our offering to support you. So with my contact details, I would like to summarize and answer the epic question. What can we do for you? What can you do for us? Actually, I tried to summarize during my talk that we have a long-lasting space heritage over decades in space with our products. Secondly, we mean it serious. We take space as a strategic market since long already, not only since the beginning of the new space era. We have a lot of experience gathered, of course. And what is really important for you to know, I'm just here as a communicator of what we have brought together, but we have founded a space community inside SHOT. So the products and solutions that I've showed you come from, for example, 5 different business units within SHOT. And we have this space community and connect to each other. And therefore, what I can offer to you, if you have questions about our solutions, which I've just presented, just feel free to contact me and I can connect you to the right people. I mean, we have much more information on all the products that you've seen, of course, for you. And secondly, we are also there for you if it comes to new ideas, new materials. You can really challenge us because we want to connect the dots, really based on our heritage, based on our experience, try to create something new together with you collaboratively, because innovation is in our DNA, so to say. And that's also my role as a business development manager. So again, for both topics, please feel free to contact and reach out. We would really pleased to support you.
Thank you very much, Boris. Really interesting presentation. A lot of products for space industry. Thanks a lot. So do you have some question for Boris here in the room? Yes, we have a question from On-Air Consulting and Solution from Stefano Pena. Stefano, if you want to ask your question by yourself.
Hi, can you hear me?
Hello. Yeah.
Hi, okay. I'm not sure that it was working. Okay, so as I wrote, concerning with the radiation hardening feature of the optical fibers, in your opinion, is something more related to the glass composition or something that can be more related to the other protections of the glass fibers, like something like buffers or jackets?
You mean your question, just to repeat that I get it correctly, you mean if it's about the glass composition, the radiation hardness, or the components to be assembled around?
Yeah, they're connected.
Yeah, okay, understood. Yeah, so for this product, we have a specialty class that is radiation hardened.
Okay, so it's glass composition. Is it just okay? Thank you.
Sure.
Thank you, Stefano. Thanks a lot. Okay, maybe I can ask a question, Boris. What is, in your point of view, the big topic of photonics in space industry for the next few years for you?
Yeah, thanks. I try to, at least touch this topic. I mean, internet from space is now the mega trend already ongoing, and with the laser communication that is going, let's say, I would say, at least as a redundancy together with RF communication, and hopefully in the future also anything possible on quantum communication. These are topics that I surely see. And then on the other side, also the topic, anything that we can improve in terms of sensor technologies for Earth observation, be it LiDAR, already mentioned today. So it would be wonderful if we can detect space debris and shoot it or so. And cameras, multispectral imaging, all these top technologies should be further improved to improve our life here on Earth.
Yeah, for sure. For sure. And are you already involved on this kind of project with SHOT?
We have a lot of different projects, and you saw the solutions that I showed. Of course, as a big company, we try to focus on high volume projects. And I can tell you that this is also a mega trend in space from my perspective. Now, with these mega constellations, we're really starting the age of higher volumes, maybe more, and hopefully more standardization compared to project business beforehand, with a lot of efforts on documentation, where the documentation has cost more than just the material and the product itself for a company. So that's really an excellent sign for the industry, I would say.
Great. Thank you, Boris. Okay, we have a question from Minaric. Axel Off, please.
Yes. Just a question on the radiation hardness for the coverage of APDs. Is this restricted to some specific technology, or is it you work there with different technology partners, or how does the cooperation look there?
I try to repeat your question so that I get it correctly. So you mean like protecting avalanche photodiodes as a detector?
Yes.
Yeah, okay. I mean, as mentioned, these products that I just showed, like the fiber optical plates radiation hardened, they are supposed to protect photodetectors. So of course, now it depends a lot on the APD design that you're using, but I know that we can do very small fibers here, so trying to match your pixel sizes and so on. I don't want to go too much into detail, but I would really like to connect to you and talk to you about it.
Okay.
Great. Thank you, Axel. Okay. Okay, so if we have no more questions, thank you again, Boris, for your presentation. Really relevant. Thanks a lot.
Thank you.
And I would like to take the opportunity to speak about micro optics with the Fabulous project, European Fabulous project. So I will share my screen. Okay, can you see my screen? It's okay. So yeah, I would like to take this opportunity to talk about Fabulous, which is an European project. So it's actually a pilot line for freeform micro optics, and it represents the full value chain and consists of Europe's leading companies and R&D organizations in the field of micro optics. So Fabulous offers a full range of services from optical design to pilot and volume production, including tooling and material selection. And yeah, I would like also to add that Fabulous launches an open call in June, so feel free to ask if you have any question. You can come back to me. And we have a beautiful promotion video for Fabulous.
I think that the sound is not working.
You can't hear the sound?
No sound, unfortunately, but let's say for the moment we can see just the pictures, okay. And Jeremy eventually will share with you the link of the video so you can have also the sound.
I will put the link in the chat. If you have any question regarding Fabulous,
yes,
please, yeah, come back to me.
Okay. Meanwhile, I see that Florian from XR Nanotech has a question. Please, Florian.
Oh yes, thanks. This was regarding the short presentation we just saw. How do you verify or test your radiation hardness of your products?
Hello, Florian. Yeah, thanks for the question. Well, it depends, I would say, on the product, but I know it, for example, for our photovoltaic modules. Here, I can tell you that already a couple of years ago, so even before that all take off, we did tests with our classes on in different institutes, so the leading institutes all around Europe, and this was massive, so we invested heavily upfront, and it really paid off because now we can make the business. But yeah, this is for the photovoltaic covers. I can't tell it now to you. Well, yeah, for the optical class, I also know that there are even, I mean, our optical classes are so much standard, for example, in the industry, to my understanding, that even some institutes that do these tests take just our classes, yeah, and do the tests for that. So we have documents that I can share. Most probably, I have to double check with the colleagues, with the product managers, but then I can make it available for you. And yeah, there's a lot of information available.
Thanks. I'll make sure to reach out to you later.
Cool.
Thanks, Florian, for the question. So thanks again, Boris, for your presentation. And now we can maybe welcome Fabrizio Preda, the CEO of Nereos. Fabrizio.
Hello to everyone.
Hello.
Good afternoon. So thanks a lot for this introduction. I will just share the screen with you. Can you see the screen? Can you?
Yes, it's perfect.
Okay, thanks a lot. So in this brief presentation, I would like to introduce a bit our company and what we do. So we develop hyperspectral cameras, and we are trying now to develop them and to target space application, in particular Earth observation and monitoring. So just a quick introduction on our company. Niros is an innovative SME company. We are a spin-off company of Politecnico di Milano University. So we are based in Milan, in Italy. And we are a pretty young company. So we incorporated it 4 years ago in May 2018. We are now in 7 people employed. So we are growing pretty fast. And we have a lot of expertise and experience in photonics. So we have more than 8 years cumulative experience in photonics, summing up all the experience of the members. What we do, we develop and manufacture novel devices for spectroscopy. So namely, we develop interferometers, spectrometers, and hyperspectral cameras. For those of you who do not know what a hyperspectral camera is, let me start by sharing with you this slide. I think it's pretty quick to understand. So hyperspectral imaging is an imaging technique in which basically for each pixel of the image that you measure, you get the entire spectrum of the light. So for example, if we compare with a standard RGB camera, as you can see, here, you can see that you have 3 bands. So with an RGB image, you have only 3 bands. You're sensitive to the red, the green, and the blue band. So we can differentiate the RGB from the multispectral imaging, where you have several bands. So you don't only have RG and B, you have many more, but still multispectral imaging is typically defined as having several discrete bands. While hyperspectral imaging instead is when you have really the entire spectrum of the light, when you have a continuous spectrum. And that's what we are developing. Actually, we have already developed a couple of hyperspectral cameras that are already on the market. One model, the black one here, you can see in the visible and near infrared spectral region, and another model for the shortwave infrared. These models are on the market since a couple of years now, and we are developing mainly, I would say, scientific applications ranging from biology to microscopy, from remote sensing and plastic sorting, food testing, and cultural heritage. So these images here are real measurements that we or our customers or collaborators have measured with our system. And you can see really the advantage of having a hyperspectral camera that does allow you to, let's say, measure more information, much more informative content with respect to what is possible to do with an RGB camera. So let's say the advantages of hyperspectral imaging is really clear, I think, with these slides. Now, there are plenty of other technologies so on the market, plenty of other manufacturers of spectral cameras, hyperspectral cameras, based on different technologies. So you can find the so-called snapshot technique, in which basically you have a 2-dimensional sensor and you have like a mosaic of different filters. So you can dedicate different portions of your sensors to different colors. So you basically build up your spectral imaging by, let's say, dividing the sensor in different colors. You can have a steering approach where you have, for example, a tunable filter or a wheel with filters. So you acquire different images, each one a different color. Or you can have a push broom, the so-called push broom technology, in which you have a dispersive element, such as a grating, that disperses the color of the light along one direction. So you have a bidimensional sensor and you dedicate one direction to the color, another direction to the space, and you scan the camera through the image to grab the entire hyperspectral data cube. So these are different possible approaches. And of course, each one of them is more suitable depending on the application you want to target. We work with another approach that we have patented in the last years. And it's the let's say the very same approach as an FTIR spectrometer, which I think most of you know. So an FTIR, or a Fourier transform infrared spectrometer works with an interferometer in front of a single pixel detector. The interferometer creates two replicas of the light that enters the device, the interferometer scans the delay tau between the two replicas so that at the single pixel you measure an interferogram, which is an intensity pattern. And the Fourier transformation of that provides you the spectrum of the light. So we are extending with our approach this methodology to the bidimensional case. So instead of a single pixel detector, we employ a bidimensional detector coupled with a camera lens. And so the interferometer scans the delay between two replicas of the scene that I'm looking at. So I scan the interferometer, I collect a stack of multiple monochromatic scenes at different delays of the interferometer. So I collect a time domain data cube. And then a Fourier transformations for each and every pixel of the detector provides the final hyperspectral data cube. So that's the approach we are following with our devices. And the advantages, let's say, of this approach are mainly linked to the very high optical throughput that an FT device can provide. So you have a very large aperture of the camera, so you don't have any slit, any grating with typically limited efficiency over a broad spectral coverage. The spectral resolution can be tunable via software. So it's really easy to tune, to vary the spectral resolution depending on the applications you want to target. The device is lightweight and compact, and it's the interferometer that we employ is very, very stable and broadband. And the fact that it's so stable, this allows us to work from the UV, from the ultraviolet portion of the light, up to 20 micron wavelengths. So it's very broadband. That's a picture of the interferometer. You can see that it's quite small compared to other interferometers you might be familiar with, such as Michelson's interferometer. So this device is very small. And so with these advantages in mind, we are trying now to reach the space, so to target space applications. And for that, recently, we have, let's say, signed a contract with ESA, following the exploiting, let's say, the Open Space Innovation Platform, the OSIP program, with the idea of developing an ultra-compact hyperspectral imager in the thermal infrared. So what I showed you before, I mean, the two devices that are already on the market reach 1.7 microns, in some cases 2.3 microns. Now, the idea of this project is to extend this spectral coverage up to the thermal infrared. We are not doing this alone. We are in a consortium together with CNR, which is the Research National Council of Italy, and BBT, which is a Czech company producing and manufacturing quite unique birefringent crystals that we need to go in this region. So the three of us are now developing, let's say, the first step of this long project. Of course, this is the very first step. In this project, this will last 1 year. We will design a proper version of the imager in the thermal infrared and test it, of course, here in the lab. There will be, for sure, other projects in the future to continue this development. Why thermal infrared? Well, thermal infrared, as you may know, is super important spectral region when you want to check your components. In the thermal infrared, you have a lot of resonances with the vibrational transitions of molecules. So you kind of have like a fingerprint, of molecules, so that uniquely identify them. And this is really important when you want to, for example, monitor volcanoes activities or earthquakes. This is a possible application. Wildfires, again, another very important application when you want to do Earth observation. Water use, for example, and Earth surface composition and change. And that's really important, for example, in this period when you want to maybe measure plastic patches or ghost nets in the oceans or marine pollutions and so on. So there are plenty of applications, as you know, for when you want to observe Earth from the space. Now, we know that there are plenty of applications, and now the first part of the project we have is now to identify which are the most promising applications that are suitable for the performances of the device that we want to develop. So we want to understand, maybe with your help as well, which are the most suitable applications so that we can then focus on them in the following steps of the project. A bit more information on this, if you have some colleagues in Vila Moura in Portugal in these days, a colleague of mine, Dr. Manzoni from CNR, which is part of this project, is also giving a talk at the 4S symposium in these days. So if you have colleagues there, maybe you want to follow up with him as well. So I thanks a lot I thank you all for this presentation and for your attention. And I'm available for any questions. Thank you.
Thank you to you, Fabrizio. I think that here, okay, I see some hands raising. I have just a comment. How we can help you, because I think helping you, we are helping ourselves, because here we are speaking about our planet. So what you put on the table are really extremely important challenges. So tell us what you need, and I think that everybody in the room are really challenged to support you to proceed. And then I see, first of all, I see Jacopo Belfi from Leonardo raising the hands, and then Tracy, and then we follow the discussion. Jacopo, first.
Yes, a question to Fabrizio, just a curiosity. And so can you tell us about the size of the different hyperspectral camera you presented, and if you see some perspective toward the miniaturization and also in view of space application? Thanks.
Yeah. Concerning the size, let's say, as you saw the picture of the interferometer, which was handheld, the hyperspectral camera is not much bigger than that. So you have to imagine like 20 centimeters long and 10 and 10, the other two dimensions. So it's quite small nowadays, even if it is not optimized for space application. This was just for ground application where the size is not so important, also the weight. Let's say the development and this project also aims at miniaturizing it. There is a lot of space for optimization. I think that this can be like a cube of 10, 10 and 10 centimeters, something like that. And the weight can be a few hundreds of grams. For sure, also connecting to Antonio's questions, we do not nowadays have expertise or how to say, strategic collaborations with a partner which is expert in mechanical or vacuum technologies that are required for space applications. So this is one thing that for sure we are looking for, is an expertise for this mechanical improvement that also comprises the miniaturization as well. The power consumption is another thing we need to look at. So we are really looking for having a partner maybe for the following steps of the project, which are expert in this sense.
Okay, interesting. Thank you.
Thank you, Fabrizio. I just follow your point, Fabrizio, and I ask Marco how we can concretely support, for example, Fabrizio in these efforts. Is in a ESA project, but I think ESA or ASI or what else. Here we are dealing with our planet. So in this case, Fabrizio raised the point about some special expertise that are not easy to find around.
Yes, thanks, Antonio. Actually, I met Fabrizio, I think, a couple of times, no? If I remember well.
Yeah, correct.
We spoke a lot. This is in the frame of just brackets. An initiative that in ASI we have for meeting the universities' indices for technology development purposes. So everybody is free to contact me. Italian partners, of course, can contact me for this kind of meeting. For specifically, for example, we are working now on an opportunity, a call for the optics roadmap, and within this roadmap, we want also to support low TRL activities. So we are working actually in these days on these new opportunities for the Italian community. Of course, this is a quite interesting technology. There are some challenges to be considered. I think in this perspective, let's say the exchanges between different expertise are fundamental. So involving people dealing with space, who knows space systems, how it works, because of course there is a problem, there is something to be understood in terms of acquisition time, if I remember well now, Fabrizio, of stability of the scene that is needed in order to use this material that is in principle very interesting. But what we can think is also to probably to change so we don't need actually to look at Earth necessarily. We can look something else in space. So to use the same technology, for example, in order for any other kind of observation that are probably more suitable for the specific capabilities of this system. A scene that is more stable in time, for example. There could be something related to in-orbit servicing or the exploration of another system based on a fixed point. So, scene, something else to be saw from we see from space.
Yeah, sure. Yeah, that's a detail I didn't have time to talk about, but that's a crucial point for sure. So in this technology, the interferometer has to be scanned. So you need time to acquire the hyperspectral image. And during this time, let's say you have to follow the image. So if you have a satellite moving around the Earth, you have to follow the same scene while you're measuring. The measurement time is on the order of seconds. So during this time, you need to track what you are looking at so that the scene is always in the same point. So these technologies, let's say, can be applied, I would say, not for survey when you have a scanning system like a push broom system or a line scanner, for example, is more for setting in something. So if you want to really sit there and study what's going on in that area, then you can track and follow that area and continue to look at that more than a survey looking for something. So yeah, but we do not want to limit to the Earth of the observation. If we find something else which is more suitable for the technology, then for sure we need these inputs for sure.
Or at least for Earth observation, but not from a very low Earth orbit. You can consider, of course, depending on the resolution on ground that you want to acquire, but you can foresee an higher orbit, let's say 800, 1000 K. But of course, you need to make a trade-off.
Yeah, sure.
Regarding the resolution and the dimensions of the scene and so on.
Okay, so Tracy, sorry for make you waiting so long.
No worries at all. And in fact, Marco just highlighted one of the questions I had, and that was about resolution. So how do you get the resolution that you're going to need? And I was wondering if you were using HAPS or if you were using LEO or if you were using higher satellites. So I was wondering about the resolution, but I was also very interested in, so I understood that you could monitor, heat sources like volcanoes and fires and whatnot. But when you mentioned water, so and then looking at the composition of water, how are you doing that? How deep can you go? How does this work? I'm very curious. I'm sorry. And maybe this is something that we can discuss later. I don't know if this is germane for the discussion now.
Yeah, sure. We can discuss later on, maybe a bit more in details. Let's say the general answer is that we want to understand that as well. So we know that by looking at in that spectral range, these are the things you can look at. So in that spectral range, you can look at volcanoes, you can look at atmosphere, you can look at gases, geology's application as well. Of course, we are still in the very beginning of the project. So we are very low in TRL, and now we just, the aim of this project is not to end up with a defined spatial resolutions as an input. You know, we want to understand which is the application we want to target, and that's the first part of this project. And once we have defined the application, we can say, okay, now we need this kind of spectral resolution. We know we have flexibility because the system that we have developed, this kind of interferometer, is independent on the spatial resolution. So we can use different optics, we can use different sensors, so we can adapt the spatial resolution without touching the spectral resolution, which is always the same. So we can really, you know, tailor then these details later on when we find the proper application. But I mean, we can discuss this in more details, of course, later on.
I would love to, you know, because there are competitive solutions that are available now, but they have their limits, and if you could extend that, especially into water, and it's really amazing. I think of hyperspectral imaging for something that's fairly close and something fairly small, like looking at plastics or perhaps looking at gases, but it's just fascinating. So I would love doing this from space and how you keep your resolution and how you track the object. Very, very interesting. So thank you so much for your presentation, Fabrizio. And thank you to Marco for your comments as well. So thank you.
Thank you. Thank you, Tracy.
And in the meantime, we have also a question from YouTube from Yoshiaki Shikata that has more or less my question, my curiosity. He's asking about which detector are you thinking to employ? I would say also, I'm really wondering because you spoke about from 3 to 15 micron, if I'm not wrong. So it's a quite crazy wavelength range. So
yeah, sure. Let's say that the.
Please.
Can you hear me?
Yes.
Okay. Yeah, the 3 to 14 micron is the wavelength range of the interferometer. Of course, the bottleneck is the sensor. The interferometer transmittance range depends uniquely on. So the interferometer is based on birefringent crystals. So we exploit birefringence. So birefringent crystals to impart a delay between two orthogonally polarized light replicas. So once you have a crystal which is transparent and birefringent in a given spectral range, that's the working range of the interferometer. And that's why one of the three partners is BBT, the Czech company that provides this kind of crystals. Then, of course, you need a detector, as correctly you say, and you can employ any kind of technology. So the interferometer can be coupled to any detector. You can think of an MCT or a bolometer, for example, that are pretty broad in spectral range. Of course, we need to select the proper detector once we identify the application as before. So the interferometer itself can be broad. Then you can couple it to an MCT or a bolometer or whatever, depending on the application.
Yes, okay. And then, I have a curiosity from my side. You know that I'm coming from laser technologies. So typically when you design a laser, you have to take care about the mechanical design. And I would say until now, also thinking on laser for satellite application, typically we have quite heavy design, monolithic design. But thinking to nano-satellites, I'm wondering how you can get compactness of the device as well a very light design. And I'm asking if you take in account, for example, to have additive manufacturing, to have a complete different approach.
Yeah, this can be totally to be evaluated for sure. As I was mentioning before, we don't have experience of space launches, so we know that you have to bear with a lot of G's, a lot of acceleration when you launch a satellite. Our experience up to now is quite impressive. Is that considering an interferometer, is that when we align it now the device we have developed for ground application, when we align the interferometer, we align it in time zero. So when you have, let's say, a dark fringe, if you have destructive interference, and when we try to launch the interferometer or to make it fall down, or when you ship it with a DHL or FedEx, the interferometer remain totally aligned. So let's say, without taking into too much, let's say, effort up to now, is already quite robust for ground applications. Of course, we need an expertise from the EPIC, community. Maybe why not for make sure that this holds still also for space applications.
Yes, maybe I can just suggest that we keep in touch, because there is an European initiative named Pulsate, where the aim of this initiative is to promote and to extend as much as possible laser advanced and additive manufacturing technologies. So design with these technologies, or to understand which are the limits of these technologies for your device, could be really fitting in this project and in the course of this project. One is opening, it's just opened last week. So we can also keep in touch.
Yeah.
And this is a message to all our participants. There are several opportunities. In this case, if somebody has to exploit or to understand something in additive manufacturing, there is a support from this, from the open course of this project also. And meanwhile, I see also Alexander from Acktar that put a question in the chat. Alexander, don't shy. Come on, you are a whole friend.
I'm not shy at all. Thank you again. A couple of questions were already answered by Marco as well as by Fabrizio. I'm still wondering about the potential application in space. I'm not clear about that due to the wavelength range. So what can be a relevant application? Also thinking maybe not for a one-time big mission, but into constellations or something like that. This is, I think, what is more interesting for like a startup as you are. I haven't yet an idea. So I just wanted to bring my curiosity in here. What can be a good application for that? But you haven't yet talked about your on-ground applications, your let's say civil applications. Maybe you can just briefly go over that.
Yeah, sure. So the list of possible application that we have found, let's say for Earth observation, is the one I showed you before. We don't have yet a clear target, so we don't have one application that we want to target. This was also this meeting an opportunity for us to hear which are the most interesting. So maybe some other people connected to the call may help. Concerning the ground application, let's say what we are working on the most in this period is the scientific application. So our main customers are now universities, research centers, or also R&D departments of corporates, of industries. The applications are really diverse. The hyperspectral imaging in general can be applied, and we are applying, and our customers are applying it to, for example, quality control in production lines, for example, when you want to perform plastic sorting. So in plastics, this is really powerful. Typically for plastics, you want to go in the sphere region between 1 and 2.5 microns. That's really, there you have fingerprints of different plastics. So you're able to sort them. Hyperspectral imaging can be applied to biology, to the study of tissues, to the study of tumoral cancer cells. We have a collaboration with let's say an hospital, a research center here in Milan, when we perform hyperspectral imaging in microscopy on tumoral tissues. We are working a lot on cultural heritage. So if you have a painting, or if you have a fresco, and you want to monitor the pigments, or if you want to monitor the degradation of the piece of art, you can perform hyperspectral imaging and detect from there which kind of pigments have been used, and by that you can to prove the authenticity of a painting, for example, or you want to date it, for example. Other applications involve food and beverage security. For food, for example, you can detect if you have foreign bodies in your food. If you want to monitor the fat content of a piece of meat, and that can be done in the infrared as well. So hyperspectral imaging is a very general tool with a lot of application. And these are the ones we are targeting for ground application. For Earth observation, we have ideas, of course, and the ideas we have are the ones we listed, but maybe also by speaking with Marco from ASI or others, we can find another application which is definitely more suitable, such as, you know, don't look at the Earth, look at the space and check for other things.
Yes, this is a suggestion to everybody. Also, if you would like to be in contact with Fabrizio as well, with all the other speakers, and maybe tomorrow you are still thinking, please reach them directly, or if you don't have the direct contact, feel free to send a mail to me or to Jérémy, and we will be extremely happy to introduce each other. And now it's time to go to another extremely dynamic entities in Padova. And I'm really happy to have here Stefano Bonora from Dynamic Optics.
Okay, hello.
Hello, yes.
Everybody. Okay, so.
Perfect, go.
You see my screen? Okay, should move out this probably. Okay, thank you, Antonio, for inviting me. My name is Stefano Bonora. I am the CEO and founder of Dynamic Optics. Today, in this short presentation, I will present us as a group of companies, the Space Factory. Us, Dynamic Optics, we work on the development of deformable optical device and also systems. And last, Thin Quantum, which is another company part of the group, which is developing quantum key distribution systems. So let's start from the parent company, the bigger one, company based in the north of Italy. And Officina Stellare started building telescopes for ground-based telescope for sky observation, but soon they become a space factory, so developing also telescope for space. And the beauty of working with Officina Stellare is that they have in-house all the chain and the manufacturing tool for building beautiful telescope with a very large size, up to about 1.5 meters. And so they can develop up to TRL-9 low cost and high performance telescope. So just to give you an example of a space application, so this is some picture of the city of Venice taken with a telescope with 1 meter resolution on ground. And in the roadmap of Officina Stellare, there is to work, and there are already a lot of active work in these fields, such as, for example, observation, laser communication, and space situational awareness. And they are already planning to build several hundreds of telescopes in the upcoming years. So second, it's us, our company, Dynamic Optics. So we build devices, optical devices that can change its own shape. And all our technology is based on the use of very thin, flexible glass membranes. So our product spans from deformable mirrors and also to deformable lenses, where we have a patented technology, and also to control system that includes all the sensors for controlling the lenses and the mirrors. What I mean is waveform sensors. So in our portfolio of applications, we work a lot, especially with the deformable lenses in ophthalmic instruments and in microscopy, where our lenses are sort of plug and play components in the microscope in order to get higher contrast in the images, which are deteriorated by optical aberrations. But we are also very active with deformable mirrors in high power lasers. So we have been supplying deformable mirrors for high peak power and high average power laser across all the world. And starting from January 2022, we've been incorporated by Officina Stellare. So our gravity is moving towards laser communication and deformable optics for telescopes. So our approach to solve the problem of correcting for optical aberration is to use gradivity. And in this slide, I would like to give you just an example of our results obtained working together in partnership with our parent company, Officina Stellare. So this is a Richiker-Kent telescope modified in order to have on the secondary mirror a deformable mirror, which is being manufactured by us. in order to correct for optical aberrations. So briefly, this is a small telescope, 300 millimeter in aperture, but you can see in this diagram on the bottom, the system when it is on and off observing a star, where you can see that when the system is off, the star is completely blurred and is jumping around. When the system is on, is well focused and placed in the center of the detector. So our interest for space optics is relative to the development of adaptive optics system for optical ground stations. So our contributes goes from the development or the supply of the formable mirrors, but also to the development of the control system for the ground stations. And also we are looking into space applications of our components. So the formable lenses and the formable mirrors improve the performances of space telescope for observation and for laser comm as well. So we are looking into space qualification of our devices. So last but not last, very important, Think Quantum is a startup as a spin-off of the University of Padua, and they carry on the experience of more 1 decade on quantum physics of the quantum communication group of the University of Padua. And they formed this spin-off a few months ago, but they already have on the market a couple of products. You can see the picture here, the modules for quantum key distribution, Alice and Bob, and also quantum random number generator, which is a proprietary technology of them. So their interest, their technology has been developed for securing optical communication, and there is, as everybody knows, a growing demand in the world for security in communication, and therefore the quantum encryption, which is physically intrinsic in this method, is something which can be very important for secure the communications. So their solutions can be applied to fiber link, so to ground communication through fibers, but also for building-to-building free space optical link, and last but not last again, for satellite, so from ground to satellite links. So the active challenges of our group are in the Earth observation in low orbit, so about improving the stability to improve the resolution of the acquired images, and also the application to SSA and SDA, to have a better resolution and capacity of debris identification from the orbit. And also in the development of onboard optical terminal for quantum keys for quantum communications, and as well, last but not last again, adaptive optics development for space application, for example, for getting better images or faster communication. So in the last slide, you have some contacts of us. You have emails. Feel free to contact us. And my last message is: we can, one of us can supply devices and products, but as a group, we can supply a full system for an optical antenna, adaptive optics correction for atmospheric turbulence, and also quantum communication. So thank you very much for your attention.
Thank you so much, Stefano. I think that it was really a challenge to summarize in so short time all the things that you do. And yeah, maybe, okay, if you can stop sharing, I think that meanwhile, Tracy raised the hands, and I think that also a lot of other people could have curiosity. Please, Tracy.
Oh, thank you so much, Antonio. So, Stefano, this was a very interesting presentation, a very low-key presentation with some very sophisticated techniques, specifically optical ground stations, where normally we think of RF ground stations. So the ability to do optical communications from terrestrial to satellite. And so there's been this ongoing issue with how do you accommodate the distortion from the atmospheric layer? Can you use your deformable mirrors for focus to help accommodate this, or have I taken it one step too far? I think I've shocked him. I think he's frozen. There we go.
Frozen.
Yeah, sorry, I couldn't hear you in the last 20 seconds.
Maybe.
Oh, I'm so sorry.
Yeah.
Repeat the question, Tracy. Maybe it was a
Stefano, I really liked your optical ground stations as opposed to RF. And I was curious if you can use your deformable mirrors and lenses as a means of compensating for the atmospheric distortion that you get going from terrestrial to satellite communications.
Yeah, this is exactly what we are trying to do and what we aim to do. And so we are participating to projects in order to be able to carry out the atmospheric turbulence correction. So in this view, we can supply the formable mirror, the wavefront sensor, and also the control system, which is the heart of the system that makes the wavefront sensor talk to the deformable mirror and carry out the wavefront compensation as fast as possible and to be very effective.
That's amazing. That's just amazing. Thank you so much, Stefano.
Thank you, Teresa.
Okay, any other question or comments? Fabrizio, do you think that are useful, the dynamics mirror from Stefano for you?
Yeah, absolutely. Indeed, we had a chat a few weeks ago in Munich, and yeah, we also know Officine Stellari here in Padova. We are also pretty close, so not too far away from us. So I think this can be a good help for sure. So definitely a good link with them.
Okay. So what we have to do for all this ecosystem, Jérémy? What we are organizing to bring all these people together?
Yeah, just maybe we have some questions, I think, in the chat before to go forward. Yeah, we have questions from
Eric.
Alexander. Yeah.
Okay, this is the last surprise for all you, but I see Eric Beckert from Fraunhofer IOF. Please.
Yes, I should know it since Stefano is a long friend of mine, but what's the biggest aperture that you are going for, and what's the Cernic resolution of your deformable mirror?
Hi, Eric. Thank you for the question. So we work with electric actuators and what we can do in terms of maximum Zernike correction. So up to now, we developed the system up to about under 20 actuators. It means in principle, we should be able to correct for about 80 modes. And in terms of aperture, we have been supplying as a product up to 15 centimeters aperture, but we have already been prototyping 20 by 20, so square mirror, deformable mirror with 64 actuators.
We are speaking about the secondary mirror, so it's correct, Stefano. The adaptive mirror is the secondary mirror of the telescope. We have some communication.
It's freezing, no?
It's freezing, yeah. Okay, maybe we are not still ready with the free space communication, and we are using old style. So we are ready to push forward to the new style. Jérémy.
Yes, yes,
thanks.
Surprise
to all the gentlemen and ladies in this meeting.
Yes, thanks, Antonio. Yeah, I would like to remind you or just let you know that we organize an important physical meeting in September, the 13th and 14th of September at ESA, European Space Agency. So it will be about space for sure, and we'll have different sessions. So about human space exploration, new passive photonics advances for Earth observation and monitoring, space-based Lidar systems, and optical links for inter-spacecraft communication. So yeah, if you want to know more about this event, I will put the link in the chat. And we're still some slots for speakers. So if you are interested by being a speaker for this event, please send me a message, or just yeah, you're welcome to participate, of course. So I will send the link in the chat, and then you can contact me if you want. Thanks a lot.
Thank you so much, Jérémy, for the great support. And I'm just looking if there is any final question or remarks. I don't see no hands raised. It was really a quite interesting journey. So let's see. We are really going to exploit all the potential of space, new space economy using photonics. And yeah, I had so many ideas brought back, And I just try to summarize. But first of all, I will really thank so much Marco, because he gave really a great vision about the third way. There is no longer the mission pull or the technology push, but there is also the space pillar. And when there is the economy, probably the things are moving a little faster. Here I just listed some of the elements that I took during this discussion. The needs of the space agencies are for peaks and advanced photonics packaging, remote sensing platforms, inter and intra-satellite communication. Communication means quantum communication. I would say this will be really the key words for the future. As well, IOCS sensor, high performance photonic gyroscope, to guarantee the routes of these and the position of these satellites. Then, okay, we discussed about multi and hyperspectral imaging for Earth observation, which really lead to a huge number of potential users. And debris detection and management. What I bring back is that there is really a huge potential. So the photonic that we had, for an example, today in this room, really we had a huge potential to provide solution, or at least competence to fulfill a lot of these needs. So I would say photonics is available and photonics is ready to take the challenge to go to space, to the low level orbits, but also to go forward to further horizons. So with these final comments, I will thank you all the speakers, from Marco to Boris to, just a moment, to Boris, to, oh my God, to Fabrizio, to Stefano, and to Ommatidia. I forgot the name. I have too many icons here.
Eduardo.
Yeah, sorry, Leonardo. And yeah, here is closing the official meeting. So we close this YouTube streaming, but who would like to remain to chat a little more, as in a usual conference, feel free to remain a little, to chat and to exchange further comments or opinion with all the participants. And for any question, don't hesitate to reach me and Jérémy. We are really more than happy to support you for any question that could arise in the future. Thank you so much.